Hi, this is Dr. Gonzalez. In this video, we're going to talk about frequency distributions. So this information, just if you're curious, is taken from Chapter 2 of Graviter and Walnew's book, Statistics for the Behavioral Sciences, 10th edition. There is a link to a PDF copy of this chapter in Canvas in case you want to go back and read the material that I took these notes from. So one of the things we have to do as researchers after we have collected data is organize and simplify that data, because data are generally collected and they're what we consider to be raw. We need to find a way to put those data in a format that makes it easier for us to get an overview of the results that we've obtained. So that's what descriptive statistics is all about, describing the data set that we have. But before we go into descriptive statistics, we're going to talk about how researchers can use things like a frequency distribution to simplify and organize their data. So what is a frequency distribution? A frequency distribution is just a tabulation, and it's organized so that you can show someone exactly how many individuals in your sample are located inside of a category from your scale of measurement. So it's usually constructed as a table or a graph, or maybe both, but it presents the same two elements either way it's presented. It's going to have a set of categories that made up your original measurement scale, and then it's going to have a record of the frequency, or how many times an individual appears in each one of those categories. So on this slide here, I'm showing you a simple frequency distribution table. It's got two parts, and those two parts are listed as columns. One column is going to show you your categories of the measurement, and it's category X, or column X in this particular slide. And then it's going to have a second column showing you the frequency. So your X column lists out all the values from the highest to the lowest that showed up in your data set. And then under the frequency column, you have a tabulation or a tally for each one of those times that variable appeared. Or in other words, how often each X value occurs in your data set. Now, if you sum up those frequencies, it should equal the N, which is the size of your sample that you're talking about. So over here in this particular example, I have X, I have 10, 9, 8, 7, 6, 5, and 4. And then my frequency over here shows me how many times that value appeared in the data set. So just by eyeballing this distribution here, I can see that there were no 5s in my data set. There was only 1 4, and there were 7 8s. So I'm able to tell you right now the mode of the data set. The mode would be 8. Because it appears 7 times, and that's the most frequent appearance of a value, and that's what the mode is. And we'll talk more about that when we get into descriptive statistics. But you can begin to see from this table a little bit about how your data are distributed through that sample. Now, we can add columns to a frequency distribution to talk more in depth about certain things. And one of the things people might often include in a frequency distribution table is the proportion, or P, for each category. So proportions describe the frequency in relation to the total number. Sometimes they're called relative frequencies. You can also have a cumulative frequency, which is where it shows as you go up a notch in your scale, how many more of your sample were added to it. Now, the sum of your proportion columns should be equal to 1, and sometimes, especially through Jamovi, you'll see instead of a sum with the P column being 1.0, they'll go ahead and convert it to a percentage for you. So the percentage would be found by just multiplying that P by 100, and now you get a percentage. So here's an example showing you what we were just talking about. We have a different distribution here. X, I had possible scores of 1, 2, 3, 4, and 5. And my frequencies, I have 2 values that occurred once. I have 2 values that occurred 3 times. And I have 1 value that occurred twice. So there's 10 altogether. And if I calculate them out to be a proportion of 10. There's our unconverted numbers. I can then convert them to percentages over here. And now you could say 30% of my respondents were a 3, another 30% were a 2, and only 10% were a 5, only 10% were a 1, etc. Now, sometimes we work with data that is so wide in its range that we need a better way to present it for our audience to be able to understand. So we might present this as what's called a group frequency distribution. And that remedies us listing out all those X values, because it would not be very simple if I listed them all out. It would actually be much more complicated and harder to interpret. So as you can see in this example here, we've created these categories, 50 to 54, 55 to 59. And over here under frequencies, this just means I only had one value that fell between 50 and 54. But if I look at the value of 80 to 84, I can see that I had 5 that fell there. So I'm able to tell my audience, or to see myself and interpret, that the category of responses that was the highest was 80 to 84 with 5 occurring. So we've got class intervals instead of individual values. Now, in a grouped frequency distribution table, you need to have about 10 class intervals. And what we mean by that, I can go back over here. These are class intervals. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Do I have 10? No, but I've got about 10, and that's usually where we want to be. Now, the width of that interval needs to be a pretty simple number, 2, 5, 10, or 20. And you'll notice those are either they're divisible by 2 or by 5. So I can divide 2 by 2, right? 2 divided by 2 is 1. I can divide 5 by 5 and get 1. I can divide 10 by 5 and get 2, etc. Now, your bottom score in the class interval needs to be a multiple of the width, and all the intervals should be the same width. So if I go back over here, you'll notice 50 to 54, if you count 50, 51, 52, 53, 54, you'll see that the width of that category is 5. And that's consistent all the way through here. So I don't want to go 90 to 100 up here at the top, because down here it's 5 between each class. Now, in a frequency distribution graph, your score categories, or your X values, are going to be listed on an X-axis, and your frequencies are going to be plotted on a Y-axis. So if I were to draw out a graph, this is my Y-axis here, and this is my X-axis here. So score categories are going to go there, and sorry, I apologize. Let me erase that. I got that backwards. So your frequencies go on your Y-axis, and your score categories would go down here. So down here, I might have 50 to 54, and then over here, or say there were 5 of those, that would be where I would plot a dot. Okay, so when the score categories are numerical scores from an interval or a ratio scale, we're going to use what's called a histogram or a polygon when we visualize these data. So in a histogram, you have a form of a bar graph, and a bar is going to be centered directly above each score or class interval. Your height of your bar is the frequency of that occurrence, and the width shows the real limits. So that means bars don't touch. I'm sorry, bars do touch. They're adjacent to each other. If they're next to each other, they're going to touch each other. So let's look at what that looks like. Here are 2 examples of frequency distribution histograms. Remember this word, because you're going to need to know that word when you go to Jamovi. So here are the raw data right there. And the bars are touching each other. You can see there's a tiny little space in there, but they're next to each other, and it'll be very different in a minute when I show you a different one. Your frequencies are plotted on your Y-axis, okay? And the number of times those scores show up are over here. That's your Y. And then your categories are down here on your X value. So on your x-axis, sorry. On this graph here, you're plotting quiz scores. So I had a quiz that could be scored, I'm assuming, from 0 to 5. And the number of students that scored a 3 is right here at 4. So there's your 3 and your 4. Down here, you've got an example of a grouped distribution. And you can see that for height from 38 to 39 inches, there were 6. And you can see that correspond right there in that bar. Now, in a distribution polygon, you've got a dot centered above each score, and that dot has a height, and that height corresponds to the frequency. And you're going to draw a continuous line from dot to connect them into a series. And so your graph is then completed by drawing a line down to the x-axis, which is 0 frequency, at each end of the range of scores. So that ends up looking, sorry, I did not mean to do that, but that ends up looking like this. So I've got my data right here. I have the possibilities of 1, 2, 3, 4, and 5, and 6 for a response, and then my frequencies are listed. And look at the number 3 response. I had 4 times that response appeared. So there's a dot at 4. You can see these other dots are here too, and then we've connected them all with a line. Same thing is true down here for this graph. This frequency polygon is showing me categories. So for the category of 4 to 5, you have in between those two a dot placed there, and it's showing me that from 4 to 5, there were 2 respondents. Now, when your score categories or X values come from a nominal or an ordinal scale, we're going to use a bar graph. So a bar graph looks just like a histogram, except that there are no sticking together of the bars. There's a big gap or space between those bars. So for a nominal scale, that space is emphasizing to your reader that your scale has separate, distinct categories. And for ordinal scales, it's telling you that I'm using separate bars because I can't assume my categories are all the same size. Because remember, for ordinal data, the distance between response 1 and response 2 and response 2 and response 3 could be different. They're not necessarily equal distances between responses. So here's an example of a personality type presented in bar graph form. So I had personality A, B, and C. And you can see that these are categories, right? They could have had a name. This could have been avoidant personality, or I don't know, a different personality here, a third different personality. But I can still interpret my frequencies from each one of those, and I can see from this graph that personality type C was the most frequent in whatever data was collected in this particular example. Now, when you can obtain an exact frequency for each score, you can make a frequency distribution graph that's exactly the same as a histogram, a polygon, or a bar graph. And we usually use that for samples. Why? We do that because a sample is much smaller than your population. A population includes all of the possible individuals out there for whatever it is you're looking at. So it's usually impossible for us to collect data or to even know the exact number of individuals and the corresponding frequency for any of those specific categories that you're dealing with. So when the exact number of individuals is not known, we use a population distribution that can be presenting relative frequency instead of the absolute number. So here's an example of relative frequency. I don't have any numbers presented here, but what I can interpret from this is that there were slightly more females than there were males. Now, if the scores in a population are using an interval or ratio scale in their measurement, we can present that distribution with a smooth curve rather than that jagged histogram or polygon. And that smooth curve provides extra emphasis that we were dealing with a distribution that's not showing the exact frequency for each category. So what does that mean? You end up looking with something like that, the normal curve, okay? So we often call that a population distribution. We call that a normal curve. And the word normal is referring to that specific shape. And that shape could be defined mathematically using a particular equation. So here you've got a distribution of IQ scores It's normally distributed, which means that it is equal on each side to a mean or a divisor, which here we're going to call that 100. And I could fold this over on itself and it would be equal in size. And then over here, I'm looking at relative frequency. In other words, if I go over here and say between 70 and 85, I don't see any particular points. I couldn't go to a specific dot and tell you anything about whatever this dot would represent between 70 and 85. It's dealing with a population. Now, researchers use words to describe a distribution, okay, instead of just listing out the characteristics. But there are characteristics that do describe the distribution of the shape of certain distributions. So we've got shape, central tendency, and variability. And we'll talk more about these when we get into descriptive statistics in a separate video. But when we talk about central tendency, we're talking about where the middle or the center of that distribution is located. And our measures of central tendency include mean, median, and mode. Then variability is talking about how well the scores are clustered around one another or how well they are spread out over a wide range. So when we're referring to the shape of a distribution, we look at a graph for that. A distribution is going to be symmetrical if the left and the right side roughly mirror each other. So if I could fold it over on itself, would it fit on top? Distributions are going to end up being skewed if you've got a pull on one side or the other. And that means you've got outliers that are stretching out the tail ends of your distribution. So what does that look like? We'll get to it in just a minute. But a positively skewed distribution, you've got scores that are piling up on the left and your tail is pulling off to the right. So it's going to look something like that in positive. That means I've got positive outliers that are over here that are pulling my distribution. And negative is going to be the opposite. I've got outliers on that side that are pulling that distribution to the left. So at the top on this particular image here, you've got symmetrical distributions. This one is a distribution that's going to have one mode. And the one next to it here is what we call bimodal. And what that means is there are two modes for that distribution. So there are two scores that are occurring with equal frequency. And then at the picture underneath, you have two examples of skewed distributions. I have that positive skew where those outliers on the right-hand side are pulling the distribution to the right. And on the other one, I have that negative skew where lower scores are dragging it to the left. Now, the relative location of where a score falls in a distribution could be described using what we call percentiles or percentile rank. And a percentile rank for a particular X value is going to be the percentage of individuals with a score that was equal or less than an X value. So that X value is described by its rank. It's going to be called that percentile. Whenever we go to find percentiles and percentile rank, we make two new columns on the frequency table. You're going to come up with the cumulative frequency, and then you're going to come up with the cumulative percentage. And each of those cumulative percentage is going to identify that percentile rank for an upper limit of a corresponding score or a class interval. So interpolation happens when we have scores or percentages that don't correspond to an upper real limit or a cumulative percentage. So you've got to interpolate to determine a corresponding rank or percentage. And interpolation is just a mathematical process we use that uses an assumption that the scores and percentages change in a regular linear fashion as you move from one to another. Okay, so it's not exact, it's data interpolation. So when you do data interpolation, a single interval is going to be measured on two separate scales. So you might have time and dollars. And we don't know the endpoints for that whole thing, but we do know the endpoints, the interval for each scale. And you're going to have an intermediate value on one of those scales. But the problem is trying to find an intermediate value on the other scale because they're not exactly the same. So when you do interpolation, you have to follow 4 steps. You've got to find the width of the interval in both scales. You've got to locate where the intermediate value is in the interval, and that's going to correspond to a fraction of the whole interval. You're going to use that same fraction on the other scale to find a corresponding position, and then you're going to use distance from the top to determine a position on your second scale. Don't worry, you're not going to be asked to do this. Just wanted you to know what interpolation was. So this is just a visual representation of interpolation. So remember, you've got two scales. I've got time and I've got pay. And I could come up with 1/2, the middle point of my time distribution, and that would be 4 hours. And then I could come over here and find the same midway point for my interpolation of pay because I had the bottom and the top values. So I was able to say the distribution ranges from $0 to $60. What is 1/2 of 60? That's going to be 30. Now I can correspond that to the 4 hours in my original time distribution. The last thing we're going to cover is stem and leaf displays. And these are ways to provide efficient methods of looking at and displaying a frequency distribution that uses a stem, which is the first digit or digits, and then a leaf using the final digits. We go through the scores one at a time. You write the leaf down, and then you write the stem down. And what you end up getting is something that looks like this. So here's my data right here. And so I take that first digit, 8, and I write it down. And then I write a 3 because I have 83. And then for 82, I go to the same 8 and I put in a 2. And there's a 5 and a 1 because somewhere in here there's an 85 and an 81. And that gives you your organization in your stem and leaf display. So in a stem and leaf display, your picture that you get is an organized representation of the whole distribution. The leaves beside each stem is a frequency, and the individual leaves are each one of the scores. That's it for frequency distributions. There will be a video that reviews your assignment that corresponds to this topic, and it will walk you through how to do a frequency distribution in Jamovi. So don't forget to print out your notes for this if you need them, and take care.